So having seen finite automaton and regular grammars, let's switch to pushdown automaton and look for an equivalent grammar. We know that regular grammar if and only if regular language, meaning given this one can come up with an equivalent finite automaton and vice versa. So which means regular grammar, regular expression and non-deterministic finite automaton, deterministic finite automaton, they are all equivalent. Now when we focus on pushdown automaton, it's clear that the class of languages accepted by pushdown automaton is superior to this. So class of languages accepted by finite automaton is clearly a subset of class of languages accepted by pushdown automaton. Because finite automaton is a special case of pushdown automaton. In this there is no stack and everything else the same. So which means whichever is regular, one can always come up with a pushdown automaton. Simply describe without a stack. That's it. But this one is superior. Therefore, we may not be able to use the regular grammar property to describe languages accepted by pushdown automaton. So we need something more, because this says regular grammar if and only if regular language. So which means we won't be able to use regular grammar property to describe this, which means some relaxation we need on the regular grammar property so that this set can be expressed using a finite set of production rules. So interestingly, we will talk about something called context free grammars, and context free grammars are equivalent to pushdown automaton. Fine. So the relaxation is the following. For regular grammars, we say S imply say AS. So this is for regular grammar. This part we want to relax. So for context free grammars, we say S implies a non-terminal implies. It could be a terminal followed by a non-terminal, or a non-terminal followed by a terminal. So it could be any combination of this. So we say S implies alpha. And what is alpha? Alpha belongs to non-terminal union terminal that star. So which means what is alpha? Alpha is a string over non-terminals and terminals. So it could be any string over this. So it could be epsilon, or so which means S imply epsilon, or S imply just a terminal, or S imply a terminal, a non-terminal, another non-terminal followed by a terminal, or S imply non-terminals. So it could be anything. So it is some string over n and t. So that's the relaxation we need. The motivation is the following. Class of languages accepted by pushdown automaton is superior to this. So naturally, regular grammar property will not be sufficient to express this. So we need some relaxation on that. And now if alpha is having the property that it is a terminal or a terminal followed by a non-terminal, then it becomes a regular grammar. So that shows that context-free grammar is a generalization of regular grammar, and regular grammar is a special case of CFG. So regular grammar is a special case of CFG. CFG is a generalization of regular grammars. Fine. So now, having given this picture, let's look at a couple of examples. So let's look at this language a power n, b power n, where n greater than or equal to 1. We know that this language is not regular, which means it is not accepted by finite automaton. No finite automaton exists. This implies no regular grammar exists. Now the question is, we know this can be accepted by a push down automaton. We are given the description. Now let's attempt a context free grammar respecting this rule. Fine. So let's look at the following. Remember, this says when you generate A, you should generate corresponding B. Otherwise, what will happen? There may be a mismatch. When we designed push down automaton, we said we scan through this and remember in a stack that this many A's have been read, and when we start reading B, we start performing pop of the stack. So that way we ensured there is a match. But now when you write a recursive rule, we should ensure whenever A is there and equivalent B or the corresponding B is also there. So the simplest string is AB. Now, if you want to generate more of them, then what I do, whenever I say A, I ensure B is also there, and in between I bring in the recursive symbol. Now that's all. This is our CFG. It is so simple and elegant. Now you want to generate say triple A, triple B, then start symbol is S. I take this, then I replace this with A, S, B. Again I replace this. Now I want to terminate. Instead of taking this, let me take this. So which means it becomes A, AB followed by this. So this is precisely the derivation for A cube, B cube. Fine. So now this says one can apply this any number of times, and when you want to stop, then use this. Remember, when you do the derivation, starting from the start terminal, you have to come to a stage where it is a string of terminals. There should not be any non-terminal in your derivation. Supposing you stop and at some point where you have a non-terminal, for example, you ask at this stage, is this part of the language? Answer is no, because the language is defined over terminals. If you find even one non-terminal, you can clearly say such a string will not be part of the language. Fine. So this clearly tells you when you come up with a derivation, you can only stop when you have a string over terminals. Then if this is equivalent to the given language, then this string is part of the language and the grammar is correct. Otherwise, the grammar is not doing the intended job. Okay, so that's the message. And just two rules capturing this infinite set. So, what is the intuition behind this? So, if you look at a string like this, now we associate this A with this B, like this it happens, right? So, whenever we generate this A, we also generate this B. Whenever we generate this, we also generate this. So, that is how we go. And when we want to terminate, we use this production to terminate. So, for any language accepted by pushdown automaton, look at sample strings and extract a pattern like this, and with that one can build a grammar out of it. Remember, if you simply write S imply AS and without bringing B, then what will happen? You may pump more A's, or the number of A's pumped through this production, we will not have control. The moment we start reading B, we lose control over number of A's, which is why whenever A is read, an equivalent B is also read. And for that matter, one can look at a string accepted by the automaton. You can observe this pattern. So with this, you can easily come up with a context-free grammar. So quite interesting topic. Let's explore more. Consider this language: a power n, b power 2n, and n is greater than or equal to 1. So the sample strings are a, b, b, a followed by this, and so on. Now you can see that a is associated with two b's, and this a is associated with these two b's. And having given this picture, let's attempt a context-free grammar similar to what we did before. So S implies the base one is AB, or S implies A, S, BB. Now every time A is generated, we generate an equivalent BB, and using this production, and when we want to stop, we use this, and we should have at least one A and two B's. So that is ensured, which means these are all my production, and n consisting of S, T consisting of A comma B, and P is this production. Start symbol is S. Okay. Now let's look at this language: a power n, b power m, where n is strictly less than m. Now the sample strings are you have a, and n and m is at least 1. So which means if you take 1a, m is at least 2. So which means it becomes bb, or it is a so many b's. If this is double a, then this should be at least 3 b's. So things like this is allowed. Now you can rewrite this one as a power n, b power n, b power k, and n is at least 1, k is at least 1. Now our m is actually n plus k. So you can look at it this way: when you have this is like a power n, b power n, this part is b power k. So this part is a power n, b power n, this part is b power k. On the similar line, this part is a power n, b power n, this part is b power k. The only condition is, apart from this, we should have at least one more b. Correct? So now, having observed this, one can develop this. We know how to generate a grammar for this, and with that we need to combine this. So we start from S, and you can even write say two non-terminals A and B, and with A I ensure A power n, B power n is generated, which means A implies A, capital A, B will ensure A power n, B power n is generated, and we need at least one, right? So I say A implies AB. So with this you get A power n, B power n. Now focus on B. With B, I'll generate B power k. So B followed by this, and we need at least one B. So we say B implies this. Now you can see that this part generates A power n, B power n, and this part generates B power k, and k is at least 1. Now often a question like this, if you pay little attention and then map it to known problems, then it is a question of plugging in appropriate subroutine. Okay, and most of the time we will be successful if we pay attention to the underlying language and extract the pattern and map it to known grammars. Fine. So this tells you that, I mean, one can always have other conditions on n and m, and one can experiment similar grammars for such questions as well. Okay, we will certainly explore as part of tutorials, assignments, and more questions of this form.